This video introduces the second part of the fundamental theorem of calculus, another way of relating derivatives and integrals. Part 2 of the fundamental theorem of calculus says that if f is a continuous function on the closed interval ab, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative for lowercase f. That is, capital F is a function whose derivative is lowercase f. The proof of part 2 of the fundamental theorem of calculus follows directly from part 1, and I'll give that proof in another video. But here I just want to make a few comments about what this theorem means. If we think of f of x as the derivative of capital F of x, then this is saying that the integral of the derivative is equal to the original function evaluated on the endpoints. I also want to comment on the phrasing any antiderivative. Suppose capital G of x is a different antiderivative for lowercase f. We know that any two antiderivatives differ by a constant, so we know that g of x has to equal capital F of x plus some constant. So if we take g of b minus g of a, that's going to be the same thing as f of b plus c minus f of a plus c. And since the constant c's subtract out to cancel here, this is just f of b minus f of a. So this difference is the same value no matter which antiderivative of lowercase f we use. And that's why we can say that capital F can be any antiderivative. Part 2 of the fundamental theorem of calculus is super useful because it allows us to compute integrals simply by finding antiderivatives and evaluating them. Finding antiderivatives tends to be really easy. Computing integrals using the Riemann sum definition is really hard. And so because of the fundamental theorem of calculus, we don't have to go through all those lengthy and tedious computations involving limits of areas of rectangles. All we have to do to evaluate an integral is find an antiderivative and evaluate it. Let's see how this works in some examples. In this first example, the antiderivative of 3x squared is x cubed. And the antiderivative of negative 4 over x is minus 4 times ln absolute value of x. We could add a plus c to make it a general antiderivative, but we don't really need it. The fundamental theorem says that we can use any antiderivative, so we might as well use the simplest one, where c equals 0. Now we need to evaluate this antiderivative on the endpoints of negative 1 and negative 5. And we usually write this as a vertical line with a negative 1 at the bottom and a negative 5 at the top to mean evaluation. In other words, the notation capital F of x between a and b means capital F of b minus capital F of a, which is what we need to compute for our antiderivative here. So now we just plug in negative 5 for x, and then we subtract what we get when we plug in negative 1 for x. In this example, you can see why it's important to write the antiderivative of 1 over x as ln absolute value of x, not just ln of x, because ln of the absolute value of 5, which is ln of 5, actually has an answer, whereas ln of negative 5 would not exist. I can simplify this expression a little bit. I get negative 125 minus 4 ln 5 minus negative 1 plus 4 ln of 1. Since ln of 1 is 0, this becomes negative 124 minus 4 ln 5. That's about negative 130.438. In this next example, we need to find an antiderivative for this expression, y squared minus y plus 1 over the square root of y. Now we can't take the antiderivative separately of the numerator and the denominator because that's just not how the quotient rule works for differentiation, so it doesn't work that way for antidifferentiation either. Instead, let's try to simplify this expression to make it look more like something we can take the antiderivative of. So I'm going to rewrite the denominator as y to the 1/2 power, and dividing by y to the 1/2 is the same thing as multiplying by y to the negative 1/2. Distributing and adding exponents, I get y to the 3/2 minus y to the 1/2 plus y to the negative 1/2. Now that's something I can take the antiderivative of just using the power rule in reverse. Y to the 3/2 becomes y to the 5/2 by adding 1 to the exponent. I divide by the new exponent. Now here I get y to the 3/2 divided by 3/2. And here, negative 1/2 plus 1 is positive 1/2. I need to evaluate this between 4 and 1. Let me simplify a little bit. And now I'll substitute in values. Now 4 to the 5/2 is the same thing as 4 to the 1/2 raised to the 5th power. So that's 2 to the 5th power, or 32. Similarly, 4 to the 3/2 is 4 to the 1/2 cubed, so that's 2 cubed, or 8, and 4 to the 1/2 is just 2, and 1 to any power is just 1. And after some arithmetic, I get an answer of 146/15. The fundamental theorem of calculus, part 2, can be stated this way. For a function capital F with continuous derivative, the integral of the derivative is equal to the original function, evaluated on the bounds of integration.